Good evening, everyone. So welcome to my YouTube channel, Master. So today we are going to see sixth lecture on linear transformation. Let's start today's session. So today we are going to start with this result. Let V and W be two vector spaces over the same field such that over the same field and same field F over the same field F and dimension of V is finite. If T be to W be a linear transformation, then nullity of T is finite and rank of T is also finite. Let's prove it. Let dimension of V is equal to n, that is finite. Let T to W be a linear transformation. Now, null T is a vector subspace of V and dimension of T is finite. So this implies nullity of T, that is dimension of null space that is less than equal to dimension of T. So this implies nullity of T so here it is nullity in so proposition it is nullity. So nullity of T is finite. Next, let B is equal to B1, B2, Bn be a basis of V, then B is nothing but a span of V. Let W belongs to W. Let W belongs to the range of T. It means T, V. This implies there exists V belongs to V such that Tv is equal, W is equal to C. Since V belongs to B, that is span of B implies there exists alpha 1, alpha 2, alpha n belongs to F such that V is equal to alpha 1 V1 plus alpha 2 V2 alpha n Vn. This implies W is equal to PV, that is P alpha 1 V1 plus alpha 2 V2 plus alpha n Vn. So that is equal to alpha P V1 plus alpha 2 PV2 alpha n CVn. So this implies W is span of PV1, PV2 up to PVn. Okay. So this implies the range of P this can by this implies dimension of this implies this is the rank of P is equal to dimension of the range P is less than n, that is finite. So this implies the rank of P is finite. So rank-nullity theorem. We let V and W be two vector spaces over the same field F, and dimension of P is finite. If P V to W, P V to W is a linear transformation. Transformation. Linear transformation. Then linear transformation then nullity of P plus rank of T is equal to dimension of B. Let's see its proof. Dimension of B is finite. So this implies by proposition that nullity of T is finite and the rank of T is also finite. Let's say nullity of P is equal to N and rank of P is equal to N. Let nullity is equal to, let's say dimension of B is equal to N and nullity of P is equal to nullity of P is equal to M. That is finite. Both are finite. Okay. Obviously, M is less than equal to N. Let B is equal to B1, B2 up to Bn be a basis for null space T. We can extend B to B dash basis of V. It means B is equal, dash is equal to B1, B2 up to Vm, Vm plus 1, Vm plus 2. Vm plus 3 up to Vn is a basis for B. We claim that V double dash is equal to Vm plus 1, Vm plus 2, up to Vn is a basis for we claim that P Vm plus 1, P Vm plus 2, and so on, Pvn is a basis for range of P. It means Pv. First of all, V dash is linearly independent. Let alpha 1 alpha 1 alpha 2 alpha n belongs to K such that alpha P Pm plus 1 let alpha n plus 1 alpha n plus 2 alpha n belongs to F such that alpha m plus 1 P Pm plus 1 plus alpha m plus 2 Pvm plus 2 and so on alpha n Pvn is equal to 0. So this implies P alpha m plus 1 Vm plus 1 alpha m plus 2 Vm plus 2 and so on alpha m Vn is equal to 0. So this implies alpha m plus 1 Vm plus 1 alpha m plus 2 Vm plus 2 up to alpha m Vn. This element will belongs to null P. But null P is nothing but the span of V because V is a basis for basis for basis for null P. So then this implies there exists alpha 1, alpha 2, up to alpha m, such that alpha m plus 1 b m plus 1 plus alpha m plus 2 b m plus 2 alpha n vn is equal to alpha 1 vn plus alpha 2 v2 up to alpha n alpha n alpha n vn. So this implies alpha 1 v1 plus alpha 2 v2 up to alpha m vn plus minus alpha m plus 1 vm plus 1 plus minus alpha m plus 2 vm plus 2 minus alpha n vn is equal to 0. As b is equal to v1 v2 vn vm vm sorry vm vm plus 1 vm plus 2 up to to vn. This is basis for b. So this implies this b is linearly independent. So this implies alpha 1 is equal to alpha up to alpha m minus alpha m plus 1 minus alpha m plus 2 is equal to, and so on finally minus alpha n is equal to 0. So this implies alpha 1 is equal to alpha 2, alpha 3, alpha m plus 1, alpha m plus 2 is equal to alpha n is equal to 0. So what is the meaning of this? This means alpha m plus 1, alpha m plus 2, alpha n is equal to 0. So this implies v double dash p vm plus 1 p vm plus 2 p vm is linearly independent. Is linearly independent. Now, gains of P, that is TV, is stand by V double dash Let W belongs to range B implies that exists G belongs to B such that W is equal to PV. B belongs to B, that is M of B implies there exists alpha 1, alpha 2, alpha m plus 1, alpha m plus 2, and so on alpha n such that V is equal to alpha 1 V1 plus alpha 2 V2, alpha m Pm, alpha m plus 1 Vm plus 1, alpha m plus 2 Vm plus 2, alpha m V1. So this implies, but this much part here, alpha 1 V1 plus alpha 2 V2 plus alpha m Vm, this belongs to nullity. So this implies W is equal to PV, that means P alpha 1 V1, alpha 2 V2, alpha m Vm plus alpha m plus 1 PVm plus 1, alpha m plus 2 PVm plus 2, alpha m PVm. But this part is 0 because this belongs to null space. So this implies W is equal to alpha m plus 1 PVm plus 1 plus alpha m plus 2 PVm plus 2. So this implies W is equal to, this implies a range of P, that is PV, is formed by P double dash. So finally, B double dash is a basis for range P is equal to P. Therefore, rank of P cardinality of B double dash, that is nothing but n minus 1. N is what is dimension of B, and M is dimension of, that is nullity of P. So this implies nullity of P plus rank of P is equal to dimension of G. So today's lecture about this, if you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you very much. We will see you for next.